In section 4, some aspects regarding what's called the crystal field splitting. The bonding in coordination compound is explained by what's called the valence bond theory, and the second one crystal field theory, and the third one ligand field theory, and the most modern is the molecular orbital theory. So valence bond theory, on the basis of valence bond theory, that hybridization is used to explain the bonding, and this theory has so many demerits. For example, a lot of assumptions. So with the central metal ion is ready with hybrid orbitals before bonding, but the why the certain metals undergo for higher they use higher orbitals, or certain metal ions use lower orbitals for hybridization, that is not explained by this theory. So a lot of assumptions we have to make. And in crystal field theory, what happens that the ligands are taken as point charges. They are point charges, and the central metal ion is surrounded by these ligands. Therefore, naturally, electrostatic force of attraction will come into play. So, according to this theory, that bonding between central metal ion and ligands are purely electrostatic in nature, and this theory takes into account what's called the crystal field splitting. In the presence of ligands, what happens? The d orbitals are split, and d orbitals, the 5 orbitals are there. And in the presence of ligands, what happens? This split into, for example, like this: 2 up and 3 down. Means the energy of these 3 orbitals are lowered, and the energy of these 2 orbitals are, that made higher. And this we call this a barycenter, and the energy difference, because it is indicated like this O. This O refers to octahedral, and in the case of tetrahedral, what happened? This T here, this situation is just inverted. So 3 orbitals top and 2 orbitals bottom, and therefore tetrahedral complex, this type of the splitting of orbitals always lead to high spin complexes, and in coordination number 4 means tetrahedral. And in these octahedral complexes, and this energy is called crystal field stabilization energy. Crystal field stabilization energy, and that energy plays a vital role in deciding the type of hybridization also. And the electron pairing, so we have the 2 energies involved. So energy required for pairing of electrons in d orbital, and also this crystal field stabilization energy. Suppose the pairing energy is greater than this. If the energy required for pairing of electron is greater, then what happens? The central metal ion should use its outer orbital. So there we come across what's called the high spin situation. On the other hand, electron pairing is less than crystal field stabilization energy. Here what happens? Central metal ion uses its inner orbital, because electron pairing can take place here very easily, and this will take place in the presence of very strong ligands like carbonyl, like that. And the ligands are now classified according to their ability to split the d orbitals, and that there we come across a series called what's called the spectrochemical series. So in this series, the ligands are arranged in the order of their ability to split the d orbitals. So on the basis of that, we can predict the type of hybridization and the type of bonding undergone by the complexes. And of course, this ligand field theory, that assumes electrostatic, there is ionic bond as well as covalent bond in complexes. And finally, in molecular orbital theory, completely that molecular orbital concepts are used. There is atomic orbitals overlap to give a molecular orbitals, and all that is the most modern situation. And as far as that our syllabus is concerned, we must restrict ourselves to valence bond theory and crystal field theory. And crystal field theory, that field, that is that ligands create the electrostatic field, and ligands only decide the type of what's called the the bonding in complexes, especially the type of hybridization in complexes. And this session is at present it is over, and we can meet in one more session, that is with another topic. Till that time, bye.